Okay, so now we're going to figure out, we're actually going to calculate the volume by figuring out how R, what the formula is for R as a function of S. And what I've done is I've redrawn the figure in this paper because the last figure was getting pretty complicated. So here are the boundaries of the region. This heavy black outline is essentially the boundary of that region. The axis of rotation is at x equal to -1, and I've rotated the region around the axis. I'm not, even though in the last video we sort of figured out what A and B was. In this video, I'm not going to assume that I know A and B, but I'm going to show you how to actually figure out A and B. Okay, so the variable S, remember, is a variable that goes along the axis of rotation. So we pick an S, we imagine that there's a plane slicing through the volume at that S. The cross section then is a circle, and R is the radius of that circle. So we could pick any point on the circumference of the circle, join the center to that point, and that would be R. And what we want to do is we want to pick a point such that we can relate R and S to the information we have, and the information we have is X and Y, and that information actually is valid only along the boundaries of the region. Thus these equations are true only, or they hold only along the boundary of the region. So what we're going to do is we're always going to pick the point where this cross section, that disk, touches the boundary of the original region. And this is really important to remember. This is where most of the mistakes are made. Occasionally it's tempting to pick this point, but that point, even though it touches the boundary of the volume we are rotating, does not touch the boundary of the original region. You have to find the point at which it touches the boundary of the original region, and that's this point. So we're going to pick this point, join that to that, and that's going to be R. And what that means is, for this point, the coordinates in the rotational coordinate system are going to be R and S. And to see that, let me construct a rectangle with that point and the origin of the rotational coordinate system as diagonals. So here's the rectangle with those 2 points the diagonal, and you can see now that this is R, this is S. So in the rotational coordinate system, that point has coordinates R and S. The next step is to figure out its coordinates X, Y in the original coordinate system, the coordinate system in which the boundary is specified. So that's the boundary. This is the original coordinate system. So I draw a rectangle with this point as one vertex, this point as the diagonally opposite vertex. This is the origin of the original coordinate system. And so now this is X and that is Y, and those are the coordinates of that point in the original coordinate system. Alright, so now what we're going to do is we're going to relate RS to XY looking at the two rectangles we drew. So it's very clear that S equals Y, and R, which is the distance from here to here, is X plus this distance. And this distance is just the distance that the rotation axis is away from the y-axis, and that's just 1. So R then is X plus 1. And now we can write down a third relationship by looking at which part of the boundary this point fell on and what the equation for that boundary is. So this point falls on the parabola, and the equation for that parabola is y equals x squared. So at that point, y must equal x squared. And these are the basic relations that's going to allow us to do this volume integral. And I can't emphasize enough, almost all of the mistakes that I've seen in using the disk method come from not figuring this out clearly, not writing down this set of equations. And this is the key. The key is to take the point at which the circumference of the disk touches the boundary of the original region. Okay. Now notice something. I have 4 variables here. I have r, s, x, y, but I have 3 equations here, which means I can pick any 3 of these 4 variables and express them solely in terms of the 4th variable. In other words, I can solve this set of 3 equations such that any 3 variables appear on the left hand side and only the 4th variable appears on the right hand side. And so we're going to do that. And the way we're going to do that is, because our variable of integration is s, we're going to ask that all variables except s appear on the left hand side. So let's see how we can do that. So let's begin with y. Okay, so I know that y is just s. So that's my first equation. Now notice s is on the right hand side. The next thing I want to do is write x equal to something that only contains y. And from this equation, I know x is square root y, and I know y is s, so x is square root s. And finally, I have r, and I know r is x plus 1, so that is just square root s plus 1. So as I said, we've taken 3 variables, written them, expressed them solely in terms of the 4th variable. All right. Now, it's pretty clear. We've solved one problem. We now know how r is a function of s. R is just square root of s plus 1. So the next thing we need to know is what the limits are on a and b. And remember what these are limits are. These are limits of s, the variable of integration. So we'll look at our final equation, or we can look at our original equation and ask ourselves, from the knowledge of the boundary that we originally rotated, can we find the smallest value of s and the biggest value of s? And we already know s is y. So all I need to know is to find the smallest value of y and the biggest value of y. And of course, if I look at this, so smallest value of y, biggest value of y, when the point slides along this curve, right? X and y are on this curve. So of course, the smallest value of y is 0, the largest value of y is 1, and that means the smallest value of s is 0, the largest value of s is 1. And so a equals 0 and b equals 1. Now we can do that even more systematically. So you can say the smallest and largest values of s are the smallest and largest value of y, the smallest and largest value of y are the smallest and largest value of x squared. And I know x is between 0 and 1, so the smallest and largest value of x squared are 0 and 1, and therefore the smallest and largest values of s are 0 and 1. The point of this is that once you get these equations right, you can figure out how r is a function of s, and you can take these equations and any limits that you see here, any bounds that you see here, or by looking at the diagram, you can figure out what a and b is. Okay, now that we've done that, all that remains to be done is to actually do the integral. So let me just say v is 0 to 1 pi r squared ds, and that's 0 to 1. Let me pull the pi out because that's a constant. R is square root of s plus 1 squared ds. And from now on, it's just a standard integral. So let me see what I can do. Pi 0 to 1, and I'm going to expand the square. Square root of s squared is just s ds. And now I can do that integral, and that integral is s squared over 2 plus 2, and to integrate square root of s, remember square root of s is the same as s raised to half. So this is 2 times s raised to 3 over 2 divided by 3 over 2 plus s. 1 integrates to s, and the limits of that are 0 to 1. And so when I substitute 0, of course, this entire term goes to 0. We don't have to worry about that. All we have to do is substitute 1, and that gets us pi half plus 1 raised to 3 over 2 is just 1. 2 divided by 3 over 2 is 4 over 3 plus 1. and then you can add up all of those numbers, and that's the volume. So that's the whole procedure for calculating volumes by the method of disks.